Then for ratio is 1.5, phase margin is 56, and damping factor is 61. So these two are coming more closer to each other. Now here you can see every time you increasing phase margin and increasing omega p2 frequency, this value is going approximately half, half, half. Okay, here it is reduced a lot actually. Now if someone asks you, you have two pole system, you have two pole system, okay, this is gm1, this is a gm2, okay, this is giving p1, this is giving you p2. Okay, now someone asks you where to bias your second pole, okay, so that you have good phase margin. So you can directly say p2 should be, omega p2 should be 3 times of omega ugb, so that you will get 72-degree phase margin. Okay, in this your settling is good, everything is good. So here you can see overshoot is almost negligible. Okay, okay, now let's see how damping factor is going to affect your transient response. Okay, so if we take this thing, so for two pole system, okay, then okay, so damping factor is greater than 1, suppose you have real poles. Okay, so real poles, so this is say damping factor, you can say greater than 1. So this is say damping factor 2, this is 1, and you have real poles, so it is very slow, now when it comes to damping factor less than 1, okay, so damping factor, say this is, now damping factor say less than 1, okay, as damping factor reduces, so it will be settle like so this is say damping factor is 0.7, okay, this is very small overshoot. So from above we can see 0.7 means this is 63-degree phase margin, 63-degree phase margin. Okay, so phase margin is 63-degree. Okay, now next, as you going to increase your or reduce your damping factor, reducing phase margin, so it will settle like this. Then further, if you reduce your damping factor, so as you are reducing your damping factor, your oscillations are increasing, your overshoot is also increasing. Okay, this is 0.37 in dB overshoot. This is increased, this is more increased, say this is your damping factor of say 0.5, this is damping factor of 0.5, this is further reduced, and say you go to damping factor of only point 1, then how it will be. So it will actually oscillate. So it will oscillate, it's keep on oscillating. Okay, so here I would like to tell you one more thing. I would like to introduce concept of gain margin, and how it is going to impact your transient response as well, which is also a important factor while considering stability of your system. Okay, so if I draw two pole system, say this is two pole system, say this is second pole, say okay, this is your P1 here, this is your P2, and so this is your 0 minus 90 minus 180. So here UGB is somewhere here, so this is your phase margin. Okay, this is magnitude, this is gain plot. Okay, now so we have seen phase margin. This is omega UGB, this is P1, this is P2, this is straight line, this is minus 20 dB per decade, this is minus 40 dB per decade. Now this is the point when phase reaches 180 degree. Okay, say let's say okay, this is the point when phase reaches minus 180 degree. Now this value of gain, this is known as gain margin. Okay, now and this is our omega axis, actually omega axis. Now what is the significance of this gain margin, okay, in transient? So this is our transient, okay. Now we have seen there are lot of ringing and increase in settling time if phase margin is low. Okay, but gain margin also plays a role. How? So suppose we have two waveforms like this output. So here gain margin 2, this is greater than gain margin 1. So in this case gain margin is higher as compared to this. If gain margin is high, settling is fast, this attenuation is fast, and if gain margin is low, this attenuation is high. So here number of ringing in green, where gain margin is high, number of ringing less than number of ringing where gain margin is low. Okay, so this is time. So in settling it has impact, so you should have a specification like minus 10 dB or minus 20 dB gain margin. So it is also a important factor in stability. Thank you.